Hi, hello everyone. So this is video number 3 on thermophysics. So this lesson we are going to cover temperature units and also thermometers. So this part is part 2 of thermophysics, which is about temperature. Okay, and first of all, we know that there are two different types of units you need to learn, which is Celsius degree and also the Kelvin scale. Also, we need to look at some very common very common thermometers in our daily life. All right, so um, the lesson time for this session is about one face-to-face lesson. All right, I try to do it in one videos. Okay, because there's not much information I need to cover actually. Okay, so here's the syllabus. All right, so and okay, first of all, we are going to talk about the temperature scale. So we know that temperature is a physical quantity describing the degree of hotness of a body. Okay, so when we say how hot a body is, there must be some objective measurements, and that measurement will use temperature to describe it. Okay, so there's some very common temperature we know. For example, your normal body temperature for human beings around 37 degrees Celsius. Okay, and there are two major units we will see in our study. One is degrees Celsius and the other is Kelvin. Of course, there are other temperature units, okay, but we are going to focus on these two only. Okay, so degrees Celsius and Kelvin. Okay, so for degrees Celsius, there are little circle there, and capital C. For Kelvin, there's only K. So which one is more common? Okay, so of course, normally when we watch weather forecast or you measure your body temperature, okay, normally we use degrees Celsius. So degrees Celsius is more daily life unit for temperature, and Kelvin is more scientific. So it's more scientific unit. All right. So for Celsius scale, we call that two fixed points. Fixed point, that means when you design a thermometer, okay, like so we know what thermometer looks like. I will go fast forward a little bit. So for example, this is mercury or alcohol in glass thermometer that you must have used this before. Okay, so this is just a very common um, thermometer in a laboratory. Okay, so to design to make, I should say, this liquid in glass thermometer, you need two fixed points. That means you need to have first two temperatures. The first one is what we call upper fixed point, which is 100 degrees Celsius. Why do we use 100 degrees Celsius? Because that's the temperature when water turns into steam. Water is the most common commodity in around us. Okay, actually, 70% of weight comes from water in our body, right? So water is very common. So we will use water as boiling point. Okay, so you can say that would be the boiling point of pure water. Okay, and the lower fixed point is 0 degrees Celsius. That's when water turns into ice. All right, so you can say that's freezing or melting point of pure water again. Okay, so that's how we recognize Celsius scale. So these are two temperatures you will see in liquid in glass thermometer. Okay, so how about Kelvin scale? Okay, Kelvin scale is a little bit different. Okay, it's more scientific, it's more theoretical. Okay, um, we need to have a big revision about kinetic theory. If you still remember, in kinetic theory, there are two major components in the internal energy of a matter. Okay, that's two components: molecular kinetic energy and also the molecular potential energy. Okay, so molecular kinetic energy is more about how fast molecules or particles moving within the matter, right? And so, and temperature is a measure of, so that's more scientific description of the temperature. So temperature is a measure of, so last time we've learned it, it's a measure of the average kinetic energy of molecules in a matter. Okay, so that means the more the faster those particles, the higher the temperature um, of the um, of the matter, right? Okay, and you need to understand the word average is very important, because last time we've learned that actually there's a distribution of the speed or kinetic energy of the particles in a matter, because they all move randomly, so there's no um, that's there won't be a single speed for every particles. Okay, each of them move at different speeds, so that's an average kinetic energy. Okay, so since that temperature measures the average kinetic energy, then a sensible question to ask is, how about when those molecules are no longer moving? So that means that the kinetic energy will drop to zero. Okay, and at that temperature, we say there should be a temperature scale equal what? Okay, so if you think about this, you can look at, okay, I try to zoom in for you. Okay, so you see that's a picture. Okay, so that's a volume. Okay, those are that volume of the gas at different temperature. So the lower the temperature and the smaller volume, because you know the volume of gas requires the gas molecule to move around to create that space. But when your temperature is dropping, then they move slowly, and so the volume they create is actually becoming smaller. Okay, so at certain point, when you extrapolate that line, you go to a temperature which is around minus 273 degrees Celsius. Okay, so that means theoretically, at such a temperature, the volume occupied by the gas or any particles becomes zero. Okay, that only happens when the molecules has zero kinetic energy, right? They are not moving at all. Okay, so that means instead of using degrees Celsius as a temperature scale, we need to invent another scale which at zero kinetic energy, zero average kinetic energy, that should be a temperature scale equal to zero. So that means zero temperature. And so that scale can't be degrees Celsius, because degrees Celsius will give you minus 273. And that zero scale, that zero temperature at the state of no movement is the scale called Kelvin scale. Okay, and that 0K is not OK, right? It's 0K. It's called absolute zero. Okay. Okay, the temperature scale is called, since you have absolute zero, so the Kelvin scale is also called absolute temperature. Okay, so you can only say a temperature scale is absolute when it's a Kelvin scale. You can't say Celsius scale is a absolute scale, right? Because at Celsius scale, it's not zero when the average KE becomes zero. Okay, so let's compare the two. Remember, when the kinetic energy, okay, of the particle becomes zero, the temperature, the theoretical temperature in degrees Celsius is minus 273. Okay, so let's say if you want to design a new temperature scale, you need that Kelvin scale. Okay, yeah, and that Kelvin scale should have a linear relationship with Celsius temperature. So we need to see what's the linear relationship here. So let's say when you have minus 273 degrees Celsius from the above graph, okay, so you will say at that temperature, that's absolute zero. Okay, so that's absolute zero for the Kelvin scale. Okay, so how about when it's a little bit warmer, it becomes like 200 minus 272 degrees Celsius, then we expect, because they vary, because both temperature scales should vary linearly. Okay, so in terms of Kelvin scale, it should always be added by 1. Okay, so how about when that Celsius scale becomes 0? Okay, so we understand. Okay, so you should plus 273 to get that's minus 273 becomes 0. Okay, the same thing should happen for the absolute scale. So that means at 0 degrees Celsius, that's equivalent to 273 Kelvin scale, right? How about 100? Okay, so you just plus 100 here. From 0 to 100, Celsius scale increased by 100 degrees Celsius, and that should be added by 100 as well. So that 373 degrees Celsius, Kelvin. So 100 degrees Celsius is equal to 373 Kelvin scale. Okay. Oh, sorry. Okay. So let's say, so you see for every Celsius temperature, okay, and the relationship with its Kelvin temperature counterpart, you just need to add that 273, because okay, the standard is when the Celsius temperature is 0 and the Kelvin is 273, so that means you always add 273 to convert a Celsius temperature into a Kelvin. Okay, so that's why we have this conversion formula. Okay, that's conversion between two scales. You get one Celsius temperature, okay, and you add 2703, and then you get the Kelvin scale, right? Okay, that's the conversion formula. Okay, so but you need to be careful when we're talking about the change in temperature, then in both scales, the change in temperature should be the same. You don't need to do the conversion formula. Why? Let's say from 0 Celsius degree to 100 Celsius degree, your temperature is increased by 100, right? So what's the corresponding change in temperature in Kelvin scale? It's also plus 100. So when you are talking about the change in temperature, so here's the keyword, the change. The change in temperature, 1 degree Celsius change in temperature equals 1 Kelvin change in temperature. You have to emphasize this is the change in temperature rather than a certain temperature. Okay, so they are different. When you're talking about the change in temperature, they are always the same. When you're talking about a particular temperature, then you need to use the conversion formula. Okay, so I hope you understand when do we need to use the conversion formula for a particular temperature, and when do we just use the same amount in the change in temperature. Okay, right? Okay, so just give you a very quick example to check your understanding. The initial temperature of a cup of coffee is 80 degrees Celsius and it cools down to 30 degrees Celsius. Okay, so you see that's 80, so that's the temperature unit that makes more sense to us, right? Because they are degrees Celsius. So 80 degrees Celsius coffee now cools down to 30 degrees Celsius in 10 minutes. All right. All right, so let's try to find the initial temperature in Kelvin. So initial temperature in Kelvin. Okay, so that's a particular temperature. So you need to use your conversion formula. So Kelvin, temperature in Kelvin equals temperature in degrees Celsius plus 273. Okay, so now your degrees Celsius is 80 degrees Celsius. Sorry. For the initial temperature plus 273, so that's 353. Okay, and the units must be Kelvin. Okay, how about the other one? So the other one's temperature, final temperature at Kelvin. Okay, I'll give you some time, 1 minute. Try to think about how can you find the final temperature in Kelvin. Possibly not a 1 minute too long. You can, if you have a lot in your mind, you can pause the video and go back to think again, and I hope you get your answer right. So I'm going to pause a little bit. So I think you will be fine. Okay, so in that case, again, you need to find the Kelvin scale. You just use your Celsius scale plus 273, so that's 303 Kelvin. Okay, so and the decrease in temperature in degrees Celsius. Okay, decrease. So 80 degree becoming 30 degree. So that means the decrease. Normally we use a change in temperature as delta T. So the delta T would just be 50 degree as decrease, right? And so the decrease is just, you can use 80 minus 30, which is 50 degree. Okay, Celsius. Decrease in temperature in Kelvin. Okay, so there are two ways to do it. So one way you say, oh, I play safe. I just use the initial temperature in K, take away the final temperature in K, then you will see that 50K. All right, so you see that 50K and the 50 degrees Celsius. Why? Because both decrease in temperature is one kind of a change in temperature. As we've said, once you are doing change in temperature, 1 degree Celsius change in temperature just equal to 1K change in temperature. So in terms of the change in temperature, okay, the value must be the same. Okay, so that means if you are really clear about this idea, and then you don't need to do the take away 353, take away 303, you can just write out, because the change in temperature is 50 degrees Celsius, then that's in Kelvin, should be also 50K as well, right? Okay, so just remember, when you are doing change in temperature, you don't need to use the conversion formula. Okay, so another question. Okay, just I will get you to read the question by yourself and try to get your answer, because it's really important to see the small details in those questions. Okay, so I'll give you 1 minute to try. You can pause the video, try to use 1 minute, spend 1 minute on this. Really read the question carefully. Okay. All right, so have you got your answer? All right, so the difference in absolute temperatures are two bodies. So here, difference in absolute temperature. So that means that that's the difference between two temperatures. So that means it's one temperature take away another. So it's another kind of change in temperature, or another kind of delta T in this sense. Okay, so how can you express the temperature difference in degrees Celsius? Okay, so some of you might think, oh, okay, if that's Kelvin, I know um, degrees Celsius is all, so Kelvin is always 273 greater than the degree Celsius. Why don't we just use 100K, take away 273? If you got this answer, okay, that means you have misconception. Possibly you have used this formula. You have used this formula here. You just try to put, okay, you need to find the degree Celsius. Oh, sorry. Okay, sorry. Just TC. All right. So you put 100 here, and you don't know this one. So that's 100 take away 273. So that's why you got -1. But this is wrong. Why? Because you are talking about the difference in temperature. So that's why you don't use conversion formula when you are talking about the difference in temperature. Okay, when you are talking about delta T1, so in symbol, you don't use conversion formula. So which one is the answer? The only correct answer is just like this. Okay, because they're about change in temperature. So delta T in terms of degrees Celsius always equals delta T in terms of Kelvin. Okay, that's it. So that's 1 minute. I hope you understand. Okay, so which of the following temperatures are impossible in the view of kinetic theory? So kinetic theory, understand, is we assume particles are in constant but random motions. Okay, they always have kinetic energy, but theoretically you might assume there's a temperature where all the particles just stop moving. So, and that temperature is absolute zero temperature. So in kinetic theory, we have the notion of absolute zero temperature. Okay, so absolute zero temperature must be, which must be the lowest possible temperature. It's the lowest possible temperature. So you can't have temperature lower than that. Okay, I'll just give you some time to think about which of the following temperatures, A, B, C, and D, is impossible. Okay, so the hint is absolute zero temperature is the lowest possible temperature. Think about what's the absolute zero temperature. So you might go back to see that. All right. So again, I think possibly 1 minute. If you need, you just spend more time to make sure you understand the idea so far. Okay, I'm going to pause the video again. Okay, so let's go back to C. Okay, so here's the lowest temperature. Remember, you can't have temperature lower than the absolute zero. Okay, so absolute zero means 0K or minus 273 degrees Celsius. Okay, so let's have a look. 273K, which is way greater than 0K. Okay, so which is way greater than 0K. Okay, 0K means the absolute zero, so which is possible. There's no upper limit for the temperature, but only a lower limit. Okay, so this is possible. How about minus 273 degrees Celsius, which is just equals to 0K, which is the absolute zero temperature. So, which is, okay, you can't say it's impossible, but that's what we call theoretically possible. And 273 degree, which is obviously greater than, so in terms of K, actually this one, you add another 273K, 273 plus 273, okay, and so that's 546K. Okay, so obviously this is greater than this is greater than 0K, so, and this is possible, minus 273K, which is less than 0K. Okay, if it's less than 0K, that means less than absolute zero. Okay, so, and which is impossible. Okay, which is impossible. You can't have a temperature, lower than the absolute zero. Absolute zero is the lowest possible temperature in the universe. Okay, that's it. Okay, so the second half of this note is about thermometers. So it's just a very brief introduction. I'm not going into details of those like the mechanism, or that means how stuff works. In the thermometer, I don't need to go to that details, but you just need to know some common ideas. Okay, so thermometer is just a measurement to measure temperature, which is easier to understand, and that's one key word. That's thermometric property. Thermometric property. That means that there's some property of the material. So it's about this material. That certain material they possesses a thermometric property. Okay, so what's the definition of things with thermometric property? That's one of its physical quantity must vary in one direction, either increase or decrease with temperature. Okay, so it's pretty hard to understand, right? So what does it mean? Okay, just give you a very brief account of the idea. Okay, so for example, in the mercury or alcohol in glass, so they will use certain liquid. Mercury or alcohol, they were put into a glass. So let's say, okay, so it's too thick. Possibly I try to, okay, so it's easier to see. Try to, oh, okay. And, okay, so let me, so for example, you have a thread of liquid which is colored in red, so you can read it. If that's silver, then it's if it's mercury, then it's silvery in color, so you can see. If that's alcohol, they would have some coloring in the alcohol to make it look red. All right. So the idea of the liquid in the glass is that this liquid have some thermal, they have such thermometric property. What's the thermometric property of alcohol, for example? It's like when temperature increase. So we understand the thermal expansion, right? When temperature increase, the volume of alcohol increases as well. So that's why it's called thermometric property. So because when temperature is increased, the volume of alcohol will be increased accordingly. And so that's why you can use this to measure the temperature. Okay, and that will happen for the mercury as well. Okay, so that's the thermometric property of the alcohol. So I just give you one example of this. Okay, so that's why thermometric material, mercury, alcohol. So how does it change with temperature? Expands with increasing temperature. That's what we call thermal expansion. Okay. And infrared. Okay, so nowadays we might use this sometimes, because sometimes you need to have a quick reading of a temperature. So it's infrared sensor. Okay, so the thermometric material is because higher the temperature, the more infrared radiation from your body. So that's why it's thermometric property. Okay, and resistant thermometer. Okay, so resistant is a um, electrical property of the metals. So we know that certain metals, all metals, they have resistance, but this resistance normally they varies with the temperature. So higher the temperature in metal, normally the greater the resistance. So that's why you use this thermometric property to design a thermometer, which is called resistant thermometer. Okay, good. So these are the thermometers. You just have a very rough idea that that's it. Okay, and always, so thermometric property is always important, of course, but it's not always true that the thermometric property will vary linearly with temperature. So it might not vary linearly. What do I mean by very linearly? That means when the temperature increase double, like okay, increase by, for example, when for every increase in the temperature, for every unit in the increase in the temperature, then the change of thermometric property is in certain proportion. But that's not necessarily true for all the materials. Okay, I will show you what do we mean by linear and non-linear variation for thermometric material in example 4. Okay, just have a quick look. Oh, sorry. Okay, here's the example 4. The graph below shows how electrical resistance of 3 different circuit elements change with temperature theta. Okay, so the horizontal axis is the temperature, the vertical axis is resistance. So here resistance is just one of the thermometric property can be used to design a thermometer. So which of the following circuit elements can be used to measure temperature? So okay, so let's see. How about the first one? Of course you can't measure temperature because for different temperature, you see for different temperature, you have the same resistance right here. Okay, so that means you can't tell the change in temperature by the change in resistance because the change resistance is just a constant. So this one can't be used to measure temperature. Okay, how about the second one? Okay, so second one is good because at different temperature, let's say at this temperature, you will have resistance like here. So that's temperature 1, then you have resistance 1, then you have another temperature, then you will have another resistance. So by measuring the resistance, you can figure out what temperature is given that graph. Okay, so this graph is good, and this is also a linear graph. Okay, so you see a straight line, linear variation between that R and the temperature. So here temperature we use theta, but I rather use T for better for more customer understanding. All right. The next, okay, for this one, the resistance drops when there's change in temperature. Is that okay? So let's see. If you have a temperature here, then you have a resistance here. Okay, and you have another temperature, then you will have another resistance. It seems okay. So every temperature will have its unique resistance, but this curve is non-linear, so it's non-linear variation. But it's non-linear variation is more complicated than the linear variation, but it works because every temperature you have resistance. So this one works, even though it's non-linear. How about number 4? So the problem with number 4 is, you see that it's not a one-directional trend, because remember we use a word here. Let's go back. In one direction. In one direction means when thermometer increases, your thermometric property either increases or decreases, but you can't have both. You can't have sometimes increase and sometimes decrease. Okay, so here's the problem. So when temperature increases, sometimes resistance increases, but then it falls back. So that's the problem. You can't have such you can't have this one as your thermometer. Okay, but I could explain a little bit more on this. So for example, if I got a resistance reading from the circuit, then there are two possible temperature, are they? So you can't tell, as this particular resistance, you can't tell which temperature it is. So that's why the number 4 is not good. It's not proper. It's not suitable for being a thermometer. Is that okay? Right? So remember, thermometric property must be in one direction, always varies in one direction with the temperature, and that direction could be increase or decrease. And also, you need to be aware that some of the variation is linear, but some are not, and both are okay. Okay, so last question is about shows how thermometric property X of a particular liquid varies with temperature. A liquid in glass thermometer filled with this liquid incorrectly calibrated with a linear scale. What would be the reading of this thermometer when X equals 1.4? Okay, I think they said, okay, someone do it incorrectly by using linear scale, but obviously you see this is not straight line, so this is non-linear. Okay, and you need to find the correct reading of this thermometer when X equals 1.4. X is just thermometric property. First of all, let's see if this is a thermometric property. Yes, because when temperature increases, that X is always increases. So that's why it's non-linear, but it's thermometric material. Okay, so we need to find out what would be 1.4. Okay, so when you try to draw a line over here, okay, you see, when it's 1.4, the temperature is around here, which looks more like a little bit halfway, greater than the halfway between 40 and 50 and 60. So that means it's something greater than 50. So the close answer to be 53 as this one. Okay, so this is the correct reading, but the question is about has been incorrectly calibrated with a linear scale. So they treat it like a linear scale. So when you treat it like a linear scale, what would be the reading? All right. So and you might see, okay, so if that's a linear scale, possibly I would just draw a straight line from 1 to sorry, it's very hard to draw a straight line by using the electronic pen. Let me have I need to insert a straight line over here. Okay, see, that's a straight line. Sorry about this. Oh, okay. Yeah, a little bit thicker to see. So normally when you calibrate a temperature, you will get your 0 and also 100 because you are going to use the melting point and boiling point of the pure water to calibrate. And if you treat it like a linear, then okay, so here's the linear. So non-linear is the true the supposed reading, but the linear is the one they have been calibrated. So linear calibration scale. Okay, so if you do that, you see 1.4 is around here, which is less than halfway, which here should be 70, so it looks like 60. Okay, so which one should be the answer? When you read the question, they said, right now your liquid in glass thermometer has been incorrectly, okay, calibrated. Okay, so that means you can't use the correct reading. You can only use the incorrect calibration on that glass, okay, on the liquid in glass thermometer. Okay, so the answer will be B. I hope that makes sense, right? But you need to understand, if you had that graph at your hand, then you know at 1.4 the correct reading is 53, but for people using that incorrectly calibrated thermometer, they don't have such graph, such thermometric graph in their hands, so they don't know, so they can only rely on the readings which are incorrectly calibrated on that thermometer, so they will give you reading 66 degrees, so that's a bit tricky, isn't it? All right, so I think that's it for all the work examples. Okay, so that's brief reviews. Okay, we have learned Celsius or Kelvin scale, and you always need to understand absolute zero, just 0K, 1 minus 7273 degrees Celsius. That means degrees Celsius is always 273, okay, less than the Kelvin scale, right? Okay, and okay, so that's conversion, and I'm not going to talk about this. Okay, so there's some key questions. Again, I'm in physics, I never give specific number of questions. You might just do question 1 and 2 and so on. And if you could do, normally if you could do half of them, and I would treat you like you have finished your homework. Okay, so you just spend for this one, because this is half and half hour for half hour plus half hour, so that means it's about 1 hour face-to-face lesson. So if you could spend around 1 hour for your revision and your homework, then that would be good enough. So you just spend 1 hour around for revision and homework. So do as much as you can, okay, within 1 hour. In more than 1 hour, just stop doing this. And that's the time you might need to spend for physics. Okay, so that's it. So we've covered 2.5 online lessons. I might give, I would see if I'm going to have another one, depending on after the meeting, the staff meeting, I will see how many lessons we can have. All right, okay, so see you later.